Hi, so we'll now be looking at the next concept, which in your booklet is covered under concept number 6, which deals with the location of roots of a quadratic. It's a very important idea. So let's start it. Let's look at it. So we have a situation in which suppose f of x is ax squared plus bx plus c. So we have a quadratic equation ax squared plus bx plus c equal to 0, and alpha beta is its roots, where throughout our discussion alpha by default will represent the smaller root. In some situations both the roots we can allow the roots to be equal also, in which case alpha is equal to beta. Otherwise by default alpha will be representing the smaller root, right? And corresponding to this equation you define the function which is f of x equal to ax squared plus bx plus c. So location of roots basically deals with imposing different kinds of conditions based on the relative position of the roots. So for example, some of these conditions could be, you might have a situation in which you want that both the roots are positive, or both the roots are negative, or perhaps one root is positive, one root is negative, both the roots are less than 2, both the roots are greater than 2, one root is less than 2, the root is greater than 2, and things like that. Other conditions could be that both the roots lie between 1 and 2, or maybe one root is less than 1 and the other root is greater than 2. Exactly one root between 1 and 2 and things like that. So we just want to take up all these cases and come up with a logic, look at the logic in which these conditions can be developed. Throughout the discussion, more than the final set of conditions, rather than remembering the final set of conditions, your focus should be on the logic according to which these conditions have been developed, right? So we'll start with the simplest cases first. The first case that you want to look at is that both roots are positive. So for both roots positive, the first condition that we impose is that the discriminant should be greater than or equal to 0, right? So first of all, the roots need to be real, only then we can ensure that they're positive. Then the second condition, since both roots are positive, their sum must also be positive. So minus b by a should be positive, which is equivalent to saying that a into b is a negative value. And third condition, since that both roots are positive, the product should also be positive. So c by a should be positive, which is equivalent to saying that a into c is positive. So these three conditions together will ensure that both the roots are positive, right? It's pretty straightforward. Our second case would be that, let's say both the roots are negative. So now for both the roots are negative, again the first condition remains the same because you still want to ensure that the roots are real. Second condition, since both roots are negative, the sum of the roots, which is minus b by a, should also be negative, which effectively says that b by a is positive, so a into b should be positive. So basically a and b should have the same sign. Similarly, since both the roots are negative, the product should still be positive. So again a and c should have the same sign, right? Again, these three conditions together will ensure that both the roots are negative. And the last case and the third case for the time being is one root is positive, so roots are of opposite sign. So roots are of opposite signs would essentially require one root to be positive and one root to be negative. Now in this case, one thought as far as the discriminant is concerned could be that since both the roots are of opposite signs, they obviously cannot be equal. So the roots first of all need to be real as well as distinct. So you cannot allow the discriminant to be equal to 0. So the first condition, of course, is that the discriminant must be positive. Then with regards to the sum of the roots, you really can't say anything. If one root is positive and one root is negative, the sum of the roots can turn out to be positive, 0 or negative depending upon the relative magnitudes of the two roots. So we can't really say about the second condition, anything about the second condition. But the third condition now obviously is straightforward. Since both one root is positive and one root is negative, the product of the roots will have to be negative, which effectively is saying that a into c should be negative. But if you observe, once you say that a into c is negative, the discriminant, which was b squared minus 4ac, if a into c is negative, then this entire value automatically is positive, right? So in the third case, in this case, although it might seem that there are two conditions, that the first is that the discriminant is positive and a into c should be negative, that is actually true. But interestingly, these are not independent conditions. The second condition, that is a into c is negative, will automatically ensure that the discriminant is positive. So you actually just need to ensure one condition. So the one condition is that, again, since roots are of opposite signs, the product must be negative. which is basically saying that A into C is negative. And as I have discussed, this will automatically ensure that the discriminant is positive. Right? So these are the first three cases which were quite simple. In the remaining cases, we'll also have to go to the idea of a function, and we'll also have to use the fact that the graph of this function will either be a parabola opening up or down. So before we go to the remaining cases, there's just one thing that I want to, general idea that we want to cover, and which will be applicable in many of the other cases. So again, if f of x is ax squared plus bx plus c, and assuming that of course that the roots, suppose I assume that the discriminant happens to be positive. So I could either have a parabola opening up or a parabola opening down, right? And since d is positive, the points at which it intersects the x-axis will be real and distinct. Now suppose there is a value k that lies between alpha and beta. Right? So this is the situation in which a is positive, and this is a situation in which a is negative. So one thing that should be observed is that over here, if I talk about the sign of f of k from what we've discussed is the function value at k, which for that we'll draw a line parallel to the y-axis. So that will intersect it somewhere over here, which means that the y-coordinate of this point is f of k. So clearly over here f of k is a negative value, and clearly over here f of k is a positive value. Right? So in both these situations, what's happening is that a and f of k, these two values have an opposite sign. One is positive and one is negative. So one interesting observation is that whenever a value k is between the roots of a quadratic expression ax squared plus bx plus c equals 0, the function value of the corresponding quadratic expression at a and k will have an opposite sign. Right? And actually the converse is also true. So if a into f of k is a negative value, that will ensure it is important to note that there is a double implication over here, which means that if k lies between both the roots of between alpha and beta, then of course this is true. But if a into f of k is negative, then that will also imply that k lies between alpha and beta, which then automatically will also imply that the discriminant is positive. So once you impose the condition that, for ax squared plus bx plus c equals 0, if f of x is ax squared plus bx plus c, once you impose the condition that a into f of k is a negative value, that will automatically ensure that the discriminant for that, the discriminant value for ax squared plus bx plus c equals 0 is strictly positive, and it will basically ensure that the value k lies between the roots of alpha and lies between the values alpha and beta. And a second observation is that if k does not lie between alpha and beta, in all of these four cases, what is happening is that, so for example over here a is positive, f of k is positive, so let's just write it down. So a is positive, or let's just observe it. A is positive, f of k is positive, a is positive, f of k is also positive again. A is negative, f of k is also negative, a is negative, f of k is negative. So in all these four cases, what is happening is that a into f of k, a and f of k have the same sign. So in all these cases, a times f of k is so whenever we require that a value k does not lie between alpha and beta, so if you want that k is greater than, k either lies beyond beta, or whether we want to impose the condition that k lies before alpha, then irrespective of whether it's a parabola opening up or down, we'll impose this condition. A into f of k should be positive. Right? So these 2 points have to be kept in mind. Whenever you want to impose a condition that k lies beyond beta or lies before alpha, then we'll say that a into f of k should be positive, they should have the same sign. And whenever you want to impose the condition that k lies between alpha and beta, we'll impose the condition that a into f of k should be negative. And just one additional thing, that a into f of k negative will automatically also ensure that the discriminant is positive, strictly positive, which is something which will not necessarily hold true over here. Just by saying that a into f of k is a positive value, that will not necessarily talk about the existence of real roots, right? So now we want that both the roots of a quadratic equation are greater than a fixed value k, right? K over here represents some fixed value. So over here again, these are the two possibilities. The graph of f of ax squared plus bx plus c might be a parabola opening up or down. So the first condition that will ensure is that first of all you should have real roots. So the discriminant must be greater than or equal to 0. The discriminant is equal to 0. The discriminant can be allowed to be equal to 0 also, because as the condition only talks about both the roots being greater than k. So both the roots could be equal and be greater than k. So for example, if you want both the roots should be greater than 1, then even if both the roots are equal to 2, the basic condition is satisfied, right? The second condition that we'll impose from what we just discussed, k over here is a value which lies before alpha, the smaller root. So a times f of k must be positive. And a third condition that we'll impose is that since both the roots are greater than the value k, the midpoint of both the roots. Now the midpoint of both the roots will actually be the x coordinate of the vertex. The midpoint of alpha and beta will be the x coordinate of the vertex. So since alpha and beta both are greater than k, the x coordinate of the vertex, which is minus b by 2a, should also be greater than k. Right? So these three conditions together ensure that both the roots of the quadratic are greater than the fixed value k. And similarly, we can now talk about both the roots being less than k. So in this case again, the first condition remains the same. First of all, you have to ensure that the roots are real. Second thing that you need to ensure is that again k lies after the larger root beta. So a times f of k must be positive. And the third condition would be that since again alpha and beta both are less than k, the x coordinate of the vertex, which is minus b by 2a, will also be less than k. Our next case is that k lies between the two roots. Another way of talking about the same case would be that one of the roots happens to be less than k, fixed number k, and the other root happens to be greater than the fixed number k. So in this, again from what we have discussed, since k lies between alpha and beta, a times f of k will have to be a negative value. So again a is positive over here, f of k is negative, and over here a is negative and f of k is positive. So in both the situations, a times f of k is definitely going to be a negative value. So that is one condition. And of course, as far as the discriminant is concerned, you need to ensure that the discriminant is positive. Since obviously the two roots cannot be equal, they have to be real, and at the same time they have to be distinct. But again, the good thing is that you do not have to separately impose the condition that the discriminant is positive. A into f of k being negative will automatically also ensure that the discriminant is positive. Next case is that you want to suppose you want a situation like this to happen, that you want both the roots to belong to a certain given interval. So maybe both the roots lie between 3 and 4 or 3 and 4, whatever. Right? So again, you have these two fixed values k1 and k2, where k1 is a smaller value, and both the roots must be contained in the interval k1 to k2. So over here again, as a first condition, I'll say that both the roots first of all must be real. In this case again, you can allow the two roots to be equal. So the two roots could be equal and be between k1 and k2. So the discriminant over here again has to be greater than or equal to 0. Right? Then k1 is a value which does not lie between the roots. So it is before alpha, it lies before alpha. So a times f of k1 should be positive. k2 is again a value which lies after beta. So a times f of k2 should also be positive. And as a last condition, you will say that since both the roots lie between k1 and k2, the x-coordinate of the vertex, which is minus b by 2a again, will also lie between k1 and k2. Our next case is one in which we'll say that we want that one root is less than k1 and the other root is greater than k2. So over here again, first of all, the roots must be real and distinct also, because obviously alpha and beta cannot be equal. You're inserting two values between them. So discriminant has to be positive. But then again, you don't actually have to apply that condition, because we'll say that since k1 lies between alpha and beta, a into f of k1 must be negative. And since k2 again lies between alpha and beta, a into f of k2 must also be negative. And any one of them will automatically ensure that the discriminant is strictly positive. We really can't say anything about the position of the vertex with respect to k1. So these are the only two conditions there. Again, we ideally want a condition which kind of covers all the four cases rather than coming up with conditions specifically for each of the four cases. And by observation, actually, you just need one condition, and that is that f of k1 into f of k2 should be negative. In each of these four cases, it's easy to see that if I look at the signs of the function values at k1 and k2, those signs, those function values, the two values f of k1 into f of k2 clearly have opposite signs, and therefore the product should be negative. And this, it turns out, will be the only condition that you really require. Right? From here, another corollary that you can come up with is that if you have again, if f of x is ax squared plus bx plus c, and you can find these two values k1 and k2 such that f of k1 into f of k2 is negative, then what you can say is that that quadratic will have exactly both the roots of that quadratic, f of x equal to 0 will be real and distinct, and also that one of the roots will lie between k1 and k2. Right, so let's just apply these ideas to different problems. One question should kind of cover all our parts, and we can kind of get comfortable with the conditions for all the cases again. Right, so let's start. First of all, again, let's just quickly look at the function that we have. So it's f of x equal to x square minus m minus 3x plus m equals 0. And since the discriminant will keep coming into the picture, let's simplify it. The discriminant is m minus 3 square minus 4m, which is m square minus 10m plus 9, which is m minus 9 into m minus 1. Right? The discriminant greater than or equal to 0 gives me m minus 9 into. So the discriminant will be greater than or equal to 0 if m is less than or equal to 1 or m is greater than or equal to 9. I will have to keep using this again and again. So this set is something which we found. So let's go to the first part. So the first part was again that discriminant is greater than or equal to 0, which is for m less than or equal to 1 or m greater than or equal to 9. Then the second condition was that since both the roots are positive, the sum of the roots, which is my m minus 3, should also be positive. So m should be greater than 3. And the third condition was that since both the roots are positive, the product of the roots must also be positive. So m should be positive. Now, and since we require all three conditions to be true, we'll have to take an intersection of these three sets. So 1, 2, 3. So if we take an intersection of all these three sets, we get m as being greater than or equal to 9. Right, so the answer for the A part simply is the set of all possible values, a set of all values which are greater than or equal to 9. for the second part, again, first of all, the discriminant must be greater than or equal to 0, so that is less than or equal to 1 or greater than or equal to 9. Both the roots are negative, so the sum of the roots, which is m minus 3, must be negative, so m must be less than 3. Both the roots are negative, so the product of the roots must still be positive. So again, if I take an intersection of 1, 2 and 3, I get that m can take values between 0 and 1. It can be greater than 0 or less than or equal to 1, not including 0 and including 1. Third condition, that the roots should be of opposite signs. From what we had seen, the only condition that is required is that the product has to be negative. So product of the roots is m and that needs to be negative, and as we had discussed, that will automatically ensure that the discriminant is strictly positive. Now in this question, there won't be an equal to 0. In this question, the a value, the coefficient of x square, is already fixed. It doesn't depend on the parameter. So anyway, it will be a parabola opening up only, right? So that simplifies things a bit. So for the d part, both the roots are greater than 2. So this must be the situation again. So what are the conditions? Again, d greater than or equal to 0. Second condition, clearly over here, what's happening is that f of 2 is a positive value. So what does that give us? 4 minus f of 2 is 4 minus 2m plus 6 plus m must be positive. So that turns to be 10 minus m must be positive. That's m should be less than 10. Right. 4 minus 2m plus 6 plus m, so that's 10 minus m, right? And the next condition is that since both the roots are greater than 2, the x coordinate of the vertex, which is minus b by 2a, so minus of b by 2a should also be greater than 2. So that gives me that m must be greater than 7. Again, intersection of 1, 2 and 3 will give me that greater than 7, greater than 7, greater than or equal to 9. So that's greater than or equal to 9 and less than 10. So m should be greater than or equal to 9 and less than 10. For the e part, again, both roots are less than 2. So this is the situation. So again, d should be greater than or equal to 0. Second condition will be that f of 2 again is clearly positive. So f of 2 again had turned out to be how much? 10 minus m. And the third condition now is that since both the roots are again less than 2, the x coordinate of the vertex, so that is m minus 3 by 2 times v by 2a, should also be less than 2. So m should be less than 7. So again, from 1 from 1, 2 and 3 we get that m must be less than 7. So less than 7, that won't have an intersection. Less than 7. Now for the f, g and h parts, since 1 and 2, the two numbers k1 and k2 are involved, we'll repeatedly require the value of f of 1 and f of 2, so let's just evaluate it. F of 1 is replace x by 1, so that's n plus 3. Of 2, again we had evaluated it before, it had turned out to be 10 minus n. right? So f of 1 is 4, f of 1 is 4 and f of 2 is 10 minus m. So now the f part says that both roots lie between 1 and 2. Right? So again, what are conditions? Discriminant greater than or equal to 0. So that will imply that second condition, f of 1 must be positive. But f of 1 is anyway a constant, so that is true for all values of m. Second condition is that f of 2 also must be positive. So f of 2 is 10 minus m. And the last condition is that, again, since both the roots lie between 1 and 2, the x coordinate of the vertex, so that is m minus 3 by 2, should also lie between 1 and 2. So that gives us that m should lie between 5 and 7. So we have to now take an intersection of all these four sets, which clearly is an empty set, because if you observe, the intersection of the first and fourth set itself is an empty set. There is no value of m which will satisfy both these conditions. So the effective intersection is a null set. There is no such value of m which will satisfy all the four conditions. So for this question, the f part, the answer is an empty set. Right? So there is no value of m for which both the roots will lie between 1 and 2. In the G part, you want that one of the roots should be less than 1 and the other root should be greater than 2. So we'll have a situation of this form. So for the G part to happen, this should have happened, but clearly this cannot possibly happen because f of 1 is a positive value. So this, we would have required f of 1 to be negative and f of 2 to be negative. But this is not true. The first condition can never be satisfied, because as you've seen, f of 1 turns out to be independent of m, and f of 1 turns out to be equal to 4. For each value of m, f of 1 is also is always going to be equal to 4. So anyway, that it is not possible for 1 to be between the roots, right? So for the G part, again, the answer is a null set. Last part from what we've discussed, you want that there should be exactly one root between 1 and 2. So for that, the condition is that f of 1 into f of 2 should be a negative value. So 4 into 10 minus m should be negative. Right, so for the last one, the answer is that the values of m should be greater than 10. Now this is a pretty interesting problem. You have a fairly complicated quadratic equation, the coefficients would be strange numbers, and you want to prove that the roots of this equation are real and distinct. Now obviously you will go through the nature of the roots method, in which you would try to show that the discriminant of this value is positive, but of course that will require a lot of algebra. I mean, the calculations would be rather tedious. So you want to try to come up with a more elegant solution. So we can use the idea of location of roots that we just discussed. So suppose I define a function f of x as x minus 2014. Right? Now, the coefficient of x square in this clearly will turn out to be 1 plus pi, which is a positive value. Right? So the graph of f of x clearly then would be a parabola which is opening up. Right? So we need to show that this graph will intersect the x-axis at two distinct points. So we can do something like this. Suppose I calculate the function value at all these points. So f of 2014. So f of 2014, this whole thing becomes 0. This first term is negative, the second term is also negative, so the overall thing is definitely positive. Then if I look at the function value of 2015, this entire term becomes 0. First term positive, second term negative, so it is negative. If I look at the function value at 2016, 0. First term positive, second term negative, pi of course is positive, so negative. And if I look at the function value at 2017, again 0, positive, positive. So we've easily been able to show that, if I take these four specific values 2014, 2015, 2016 and 2017, the function value at these 4 points, I've been able to determine the signs of all these expressions. But now if you think about it, what must be happening? The graph of this function is a parabola opening up, there's no doubt about that. Right? At 2014, the function value is positive, and at 2015 and 2016, the function value is negative. But if that is the case, then 2015 and 2016 must necessarily be between the roots. There is no other way. And since 2014 and 2017, the function value is positive, 2014 must be over here, and 2017 must be over here. So clearly the only way that these four conditions are satisfied is if something like this must be happening, which obviously tells you that there are two real and distinct roots of the equation, because there must be these two real and distinct points at which the graph is intersecting the x-axis. In fact, you can say something more also. You can say that one of the roots lies in the interval 2014 to 2015, and the second root lies in the interval 2016 to 2017. Right, so we have this location of roots problem. It's a pass ID problem. So again, it's a pretty straightforward problem in the sense that you just kind of have to apply the three conditions. Both roots are real and less than k condition. So we can kind of follow that approach. So again, first condition would be that the discriminant is greater than or equal to 0. Right. So that will give you that 4a square minus that gives us our first condition that a must be less than or equal to 3. The second condition is that again it's already a parabola opening up, so f of 3 must be positive. As a quadratic inequality, so you can use the wavy curve method. This turns out to be the solution set. And last condition again is that since both the roots are less than 3, the midpoint of the vertex, the x coordinate of the vertex, which is minus b by 2a, that will be 2a by 2, should also be less than 3. So again 1, 2, 3, you have to take an intersection when you take an intersection of all these three sets, you'll be left with a less than 2. So again, this is a pretty straightforward problem. You have a location of roots problem. You want that the roots first of all should be real and distinct, and both the roots alpha beta should be greater than 3. And again, the x square coefficient is anyway positive, so it's a parabola opening up. So in terms of the 3 conditions, you'll first say that the discriminant now is strictly positive because you want the roots to be distinct. Second, again, since both the roots are greater than 3, f of 3 must be positive, it's a parabola opening up. And third condition would be that since both the roots are greater than 3, the minus b by 2a value should also be greater than 3. Right? Again, solve them simultaneously, you will get your set of values of k. And from that you can figure out it should actually say the smallest integer value. Right? Let's use a slightly different approach to this problem. Let's try to find the structure of the roots. So the discriminant over here is 64k square minus 64 times k square minus k plus 1. So that's 64k minus 1. So the roots themselves are given by 8k plus minus 8 under root k minus 1 by 2. Right, so that is 4 common k plus minus under root k minus 1. So clearly, since alpha represents the smaller root, first of all, of course, I'll have to say that since I want real and distinct roots, this k minus 1 needs to be something which is positive. So that gives me a condition that k must be greater than 1. Okay. Now, simple observation is that obviously, given that k is greater than 1, the larger of these two roots, the smaller root will be 4 into, and the larger root will be 4 into. So if you want that, over here, in fact, what you want is that the value of the roots should be at least 3. So we want, the condition effectively over here is that both the roots must be greater than or equal to k, right? So over here now we can simply say that as long as you can ensure that the smaller root, which is this particular value, as long as this smaller root is greater than or equal to 3, that will automatically ensure that the larger root, the larger root is this plus sign. So as long as the smaller root is greater than or equal to 3, the larger root automatically will be greater than 3. Right? So we just have to impose that alpha is greater than or equal to 3. Right, so you get this inequality which you can then square on both sides. So 16k square plus 9 minus so we're getting factors 150. Sorry, this should have been 4 over here. Sorry, 16. 4k minus 3 is written equal to 4 root k minus 1. So we get minus 24 minus 16, so that will be minus 14, and 9 plus 16 plus 45, which is turning out to be equal to this interestingly is turning out to be a perfect square, so it's 4k minus 5 whole square. And obviously, this condition itself will be true for all possible values. Okay, so this is true for all possible values of k. Right. You therefore just have to take a condition of the conditions 1 and 2. So from 1 and 2, k belongs to the set 1 to infinity, and of course we have been asked to kind of find the smallest integral value of k. So given that k lies in the interval 1 to infinity and k cannot be equal to 1, so the smallest integral value of k must obviously be 2. Right, so this is a slightly different approach. You would have got the same answer even if you had used the set of conditions that we've already developed. In fact, that might have been easier. So this finishes the concept on location of roots.